if two functions are multiplied by one another, right, u times v, I know that the derivative of that, everybody gets a turn, right? It's u prime v plus u v prime. So things like x squared e to the x get turned into 2x times e to the x plus x squared times e to the x. And things like x square root of x should get turned into 1 square root of x plus x 1 over 2 root x. Here's the derivative of x to the 1/2. We've seen it a bunch this semester already. And this just follows the product rule. The derivative of the first factor is 1, and the second factor gets left alone, plus the first factor gets left alone, and I take the derivative of the second factor. Right? Each factor has its turn having its derivative taken, and then I add up the results. If I simplify this, right, this is x. I'm dividing by x to the 1/2. So the result is x to the 1/2. Right? This is x to the first. This is x to the 1/2. And I'm dividing them. So 1 minus 1/2 is 1/2. So that's root x plus 1/2 root x, or 3/2 root x. These are the same term, so I can add their coefficients. 1 plus 1/2 is 3/2. So this is an easier way of writing all this mess. And I find that this is x to the 1/2. These have the same base. So this is really just x to the 3/2, right? 1 plus 1/2 is 3/2. And when I take the derivative, I should get 3/2 as a coefficient. X to the 3/2 minus 1 is 1/2. So 1/2. Hey, worked out okay. So there are multiple ways to kind of get there, right? I can use the product rule here, or I could just simplify this expression, and if I simplify that expression, I can just use the power rule like I always have. All roads, though, should lead to Rome, right? If I'm performing kind of like mathematically legal operations, right, then I should always kind of wind up in the same place. And I'm not going to tell you how to kill your dragons, right? If I've got something terrifying my country, right, and you are the brave knight that is going to be doing the dirty work, I'm not going to say like, oh, go and kill the dragon, but I'd really like it if you use like a mace. I know you like the sword, but a mace would really be cool. When I'm telling this story to my future children, I'm going to say, oh man, that night they used a mace. I don't care, right? Both of these weapons are going to kind of get you to the same place, and that's what's important, right? That I am comfortable here enough that I can find the derivative of this function, and so that's what I'm concerned about. But we might ask ourselves, well, that works out really well if I have two things multiplied by one another, but what if I did something like this? What if I had like 4 functions multiplied by one another? And I wanted to know what y prime was. Well, I could certainly take this expression and try to make it look different the way that I could have here, right? I could take the time to multiply all of these expressions out, and then I would just have a regular old polynomial, and it would be really easy to differentiate. And so everybody raise your hand if you want to multiply all these out. Yeah, I don't want to either. Right? It's going to be a lot easier to be able to take the derivative of 2x plus 1. It's 2. The derivative of 3x minus 4 is 3. The derivative of x squared plus 1 is 2x. The derivative of 9x plus 7 is 9. I know the derivatives of these factors individually, and I want to be able to kind of tie together a derivative using these little pieces that make up the product in general. It turns out, though, that this is super easy. If we think about the product rule in this same kind of context of every factor gets its derivative taken and everything else gets left alone, that's exactly the way that it's going to work on a large scale, right? So if I had u times v times w, I think that's going to go to u prime vw plus u v prime w plus u v w prime, right? There's one prime in each of these expressions, right? I'm going to take the derivative of the first factor, and the second and the third ones just get left alone. And then I'm going to add what happens if I take the derivative of the second factor and leave the first and the third one alone. And then I'm going to see what happens if I take the derivative of the third factor and I leave the other two alone. Right? Every factor has its turn having its derivative taken, right? Just like good boys and girls. Right? We'll take turns. And this is true if we think about the context at large, right? This is u times vw. So if I want to think about the product rule, that's u prime, and then vw is left alone, right? This is u times vw. So if I want to use the product rule, it's the derivative of the first thing times the second thing left alone. Plus, the first thing gets left alone, and I take the derivative of the second thing. And the derivative of vw, well, how do I do that? I'm going to have to use the product rule because it's a product. So I'll take the derivative of the first thing and leave the second thing alone and add the first thing left alone times the derivative of the second thing. And then if I distribute this u through, we find that we get to the same place. So this idea fits in with exactly what happens if we kind of work it out in general. This is the general product rule. Right? So we can think about the product rule as it would apply to any old product, not just the product of two things. So if we go back and try to tackle this example in particular, we're going to find that y prime is, let's see, 2x plus 1's derivative is 2, and everything else is going to stay exactly the same. Right? 3x plus 4, x squared plus 1, 9x plus 7. And then I'm going to add, right? Now 3x minus 4 gets its derivative taken. So 3, and everything else stays the same. Right? 2x plus 1, x squared plus 1, and 9x plus 7, it's not their turn. And now, let's say I did the first one, I did the second one, and now it's x squared plus 1's turn to have its derivative taken. So plus 2x. And then everything else stays the same. 2x plus 1, 3x minus 4, 9x plus 7. And there's only one factor left. 9x plus 7's derivative is 9, and then everything else stays the same. 2x plus 1, 3x minus 4, x squared plus 1. And now I'm done. So here it is, as messy as it is. That's what the derivative is. I don't want to simplify it any. It looks painful. But that was a lot easier than coming up here and multiplying all of this out and then taking a derivative, right? Yeah.
Is it possible, since there's 4 of them, to FOIL the first 2 and then FOIL the second 2, and just to make it a little easier?
Yeah, you could do that if you wanted, right? So if I wanted to, I could kind of distribute these together if I wanted, and then it'd be easier. But if all I'm interested in what's happening like at a point, right? Here is a description of what's happening for any x, and it's kind of big and unwieldy. But if I wanted to say something like, find y prime when x is 1, this is going to be just fine, because I can plug 1 into this, and it'll be really easy, right? It's going to be 2 times 7 times 2 times 15, 16. 9 plus 7 is 16. Okay? And plus, right? I could plug this into a calculator really easy, just letting x be 1, and it's going to spit out a number, and that's easy enough to do. Just leaving it this way isn't maybe the most friendly way of writing a derivative, but if I wanted to evaluate it, this is fine. It's going to evaluate the exact same as something that's simpler. So I'm not overly worried about it being complicated, especially since it was so much easier to find than having to do all of the algebra and the arithmetic of multiplying out all of those other polynomials. So I'm a little happier.